everyone, my name is Anya, and today on Math and Science Concepts I will be talking about Newton's first law of motion, inertia. But before we begin, make sure to like, share, and subscribe, and hit that notifications bell so that you never miss another one of my informative videos. So let's begin. Aristotle and motion. Aristotle divided motion into two main classes, natural motion and violent motion. We shall briefly consider each, not as study material, but only as background to present-day ideas about motion. Aristotle asserted that natural motion proceeds from the nature of an object, dependent on what combination of the four elements, earth, water, and air, and fire, the object contains. In his view, every object in the universe has a proper place, determined by this nature. Any object not in its proper place will strive to get there. Being of earth, an unsupported lump of clay properly falls to the ground. Being of air, an unimpeded puff of smoke properly rises. Being a mixture of earth and air, but predominantly earth, a feather properly falls to the ground, but not as rapidly as a lump of clay. He stated that heavier objects would strive harder to get to their position in the universe. Hence, argued Aristotle, objects should fall at speeds proportional to their weights. The heavier the object, the faster it should fall. Violent motion, Aristotle's other class of motion, resulted from pushing or pulling forces. Violent motion was imposed motion. A person pushing a cart or lifting a heavy weight imposed motion, as did someone hurling a stone or winning a tug of war. The wind imposed motion on ships. Flood waters imposed it on boulders and tree trunks. The essential thing about violent motion was that it was externally caused and was imparted to other objects. They moved not of themselves, not by their nature, but because of pushes and pulls. To sum up, Aristotle taught that all motions are due to the nature of the moving object, or due to a sustained push or pull. Provided that an object is in its proper place, it will not move unless subjected to a force. Except for celestial objects, the normal state is one of rest. Aristotle's statements about motion were a beginning in scientific thought, and although he did not consider them to be final words on the subject, his followers for nearly 2,000 years regarded his views as beyond question. Implicit in the thinking of ancient, medieval, and early Renaissance times was the notion that the normal state of objects is one of rest. Since it was evident to most thinkers until the 16th century that the earth must be in its proper place, and since a force capable of moving the earth was inconceivable, it seemed quite clear to them that the earth does not move. And now we are continuing on to Copernicus and the moving earth. It was in this intellectual climate that the Polish astronomer Nicholas Copernicus formulated his theory of the moving earth. Copernicus reasoned that the simplest way to account for the observations of the sun, moon, and planets through the sky was to assume that the earth and the other planets circle around the sun. For years, he worked without making his thoughts public, for two different reasons. The first was that he feared persecution. A theory so completely different from common opinion would be surely taken as an attack on established order. The second reason that was he was having grave doubts about it himself. He could not reconcile the idea of a moving earth with the prevailing ideas of motion. Finally, in the last days of his life, at the urging of very close friends, he sent his De Revolutionibus to the printer. The first copy of his famous exposition reached him on the day he died, May 24, 1543. In 1543, Nicholas Copernicus proposed that the Earth rotates on its axis while the celestial sphere remains stationary. He also placed the Sun at rest near the center of the celestial sphere, while the Earth and other planets orbited around the Sun. Copernicus's heliocentric theory could account for the motions of the stars, Sun, and planets about as well as Ptolemy's theory did. It also helped explain certain features of the planetary motion that were mysterious in Ptolemy's model. However, the idea that the Earth moved was too revolutionary for most of Copernicus's contemporaries. While Copernicus believed that his model represented the real motions of the universe, most of his readers denied the Earth's motion and accepted Copernicus's theory as nothing more than a useful mathematical device. So now we shall move on to Galileo and the Leaning Tower of Pisa. Galileo, in early 17th century, gave credence to the Copernican view of a moving Earth. Galileo was the first to provide conclusive refutation through observation and experiment, and Galileo easily demolished Aristotle's falling body hypothesis. Between 1589 and 1592, Galileo Galilei is said to have dropped unequal weights of the same material from the Leaning Tower of Pisa to demonstrate that their time of descent was independent of their mass. According to a biography by Galileo's pupil Vincenzo Vinavini, composed in 1654 and published in 1770, Galileo discovered through this experiment that the objects fell with the same acceleration, proving his prediction true, while at the same time disapproving Aristotle's theory of gravity, which states that objects fall at the speed proportional to their mass. Though Viviani wrote that Galileo conducted repeated experiments made from the height of the Leaning Tower of Pisa in the presence of other professors and all the students, most historians consider it to have been a thought experiment rather than a physical test. So now this brings us to Galileo's inclined planes. Aristotle was an astute observer of nature, and he dealt with problems around him rather than with abstract cases that did not occur in his environment. Motion always involved a resistive medium such as air or water. He believed a vacuum to be impossible, and therefore did not give serious consideration to motion in the absence of an interacting medium, that is, a vacuum. That is why it was basic to Aristotle that an object requires a push or pull to keep it moving. And it was this basic principle that Galileo denied when he stated that if there was no interference with a moving object, it will keep moving in a straight line forever and ever. No push, no pull, or force of any kind is necessary. Galileo tested this hypothesis by experimenting with the motion of various objects on plane surfaces tilted at various angles. He noted that balls rolling on a downward slope picked up speed, while balls rolling on an upward slope lost speed. From this he reasoned that the balls rolling along a horizontal plane would neither speed up nor slow down. The ball would finally come to a rest, not because of its nature, but because of friction. This idea was supported by Galileo's observation of motion along smoother surfaces. When there was less friction, the motion of objects persisted for a longer time. The less the friction, the more the motion approached a constant speed. He reasoned that in the absence of friction or other opposing forces, a horizontally moving object would continue moving indefinitely, forever and forever. This assertion was supported by a different experiment and another line of reasoning. Galileo placed two of his inclined planes facing each other. He observed that a ball released from a position of rest at the top of a downward sloping plane rolled down and then up the slope of the upward sloping plane until it almost reached its initial height. He reasoned that only friction prevented it from rising to exactly the same height. For the smoother the planes, the more near the ball rose to the same height. Then he reduced the angle of the upward sloping plane. Again, the ball rose to the same height, but it had to go farther. Additional reductions of the angle yielded similar results. To reach the same height, the ball had to go farther each time. He then asked the question, if I have a long horizontal plane, how far must the ball go to reach the same height? The obvious answer was forever. It will never reach its initial height. Galileo analyzed this in a still another way. Because the downward motion of the ball from the first plane is the same for all cases, the speed of the ball when it begins moving up the second plane is the same for all cases. If it moves up a steep slope, it loses its speed rapidly. On a lesser slope, it loses its speed more slowly and rolls for a longer time. The less the upward slope, the more slowly it loses the speed and more rolling time it has. In an extreme case in which there is no slope at all, that is when the plane is horizontal, the ball should not lose any speed. In the absence of retarding forces, the tendency of the ball is to move forever, without slowing down. We call this property of an object to resist changes in motion inertia. Galileo's concept of inertia discredited the Aristotelian theory of motion. Aristotle did not recognize the idea of inertia because he failed to imagine what motion would be like without friction. In his experience, all motion was subject to resistance, and he made this fact central to his theory of motion. Aristotle's failure to recognize friction for what it was, namely a force like any other force, impeded the progress of physics for nearly 2,000 years, until the time of Galileo. An application of Galileo's concept of inertia would show that no force is required to keep Earth moving forward. The way was open for Isaac Newton to synthesize a new vision of the universe. And this brings us to the main topic of this video, Newton's first law of motion, the law of inertia. Every object continues in a state of rest or uniform motion in a straight line with the same speed unless acted upon by an external force. The key word in this law is continues. An object continues to do whatever happens to be doing unless a force is exerted upon it. If it has rest, it continues in a state of rest. This is nicely demonstrated when a tabletop is skillfully whipped from underneath dishes on a tabletop, leaving the dishes in their initial state of rest. This property of objects to resist changes in motion is called inertia. The tendency of things to resist changes in motion was what Galileo called inertia. Newton refined Galileo's idea and made it his first law, appropriately called the law of inertia. So now, if an object is moving, it continues to move without turning or changing its speed. This is evident in space probes that continually move in outer space. Changes in motion must be imposed against the tendency of an object to retain its state of motion. In the absence of net forces, a moving object tends to move along a straight line path indefinitely with the same speed forever. Changes in motion are produced by a force or combination of forces. A force, in the simplest sense, is a push or pull. Its source might be gravitational, electrical, magnetic, or simply muscular effort. When more than a single force acts on an object, we consider the net force. For example, if you and a friend pull in the same direction with equal forces on an object, the forces combine to produce a net force twice as great as your single force. If each of you pull with equal forces in opposite directions, the net force is zero. The equal but oppositely directed forces cancel each other out. One of the forces can be considered to be negative of the other, and they add algebraically to zero with a resulting net force of zero, just as +1 - 1 equals 0. So, inertia is a law that describes the tendency of an object to resist changes in its motion. No force, no change. If an external force does not act on an object, it will stay at rest or continue moving in a straight line as a constant speed, just as it was before. And mass and inertia. The amount of inertia an object has is directly related to its mass. Inertia and mass are the exact same thing. It's just different words for the same thing. So now moving on to the equilibrium rule. The equilibrium rule is the sum of the forces equals 0, with the sum sign standing for the sum of, and F standing for the forces that act on the object. If you take a string around a 2-pound bag of sugar and hang it on a weighing scale, a spring in the scale stretches until the scale reads 2 pounds. The stretched spring is under a stretching force called tension. The same scale in a science lab is likely calibrated to read the same force as 9 newtons. Both the pounds and newtons are units of weight, which in turn are units of force. The bag of sugar is attracted to Earth with a gravitational force of 2 pounds, or equivalently 9 newtons. Hang twice as much sugar from the scale, and the reading will be 18 newtons, or 4 pounds. Note that there are two forces acting upon the bag of sugar: the tension force, acting upward, and the weight acting downward. Now, these two forces are applied by the string and the earth. Hence, the bag remains at rest because the two forces on the bag are equal and opposite, and they cancel to 0. In accord with Newton's first law, no net force acts on the bag. We can look at Newton's first law in a different light: mechanical equilibrium. When the net force on something is 0, we say that something is in mechanical equilibrium. In mathematical notation, the equilibrium rule is the sum of the forces equals 0. The sum of is standing of the vector sum of, and the big F stands for forces. For a suspended object at rest, like the bag of sugar in our example, the rule says that the forces acting upward on the object must be balanced by other forces acting downward to make the vector sum equal 0. We see that the forces are equal to 0 in the equilibrium rule because the forces balance out. Now here I have an example for you to demonstrate the equilibrium rule. We have two people, Burl and Hewitt, on their sign painting scaffold. The sum of the upward weights and tensions is equal to the sum of their weights plus the weight of the scaffold. Note how the magnitudes of the two upward vectors equals the magnitude of the three downward vectors that you can see in this diagram here. Net force on the scaffold is 0, so we say it is in mechanical equilibrium because these forces balance each other out. I have a couple more examples for you. Consider a book lying at rest on a table. It is in equilibrium. What forces act on the book? One force is that due to gravity, the weight of the book. Since the book is in equilibrium, there must be another force acting on the book to produce a net force of 0, an upward force, opposite to the force of gravity. The table exerts this upward force. We call this upward force the support force. This upward support force, often called the normal force, must equal the weight of the book. If we call the upward force positive, the downward weight is negative, and the two add to become 0. The net force of the book is 0, and another way to say the same thing is the sum of the forces equals 0. That is another example of the equilibrium rule. I have one more thing for you before we move on. Rest is only one form of equilibrium. An object moving at a constant speed in a straight line path is also in equilibrium. Equilibrium is a state of no change, not just rest. A bowling ball rolling at a constant speed in a straight line is also in equilibrium until it hits the pins. Whether at rest, static equilibrium, or steadily rolling in a straight line path, dynamic equilibrium, the sum of the forces equals 0, and there can be so many other examples in equilibrium. Following from Newton's first law that an object under the influence of only one force cannot be in equilibrium, net force couldn't be 0. Only when two or more forces act on it can it be in equilibrium. We can test whether or not something is in equilibrium by noting whether or not it undergoes changes in its state of motion. And now to our final part, the moving Earth. When Copernicus announced the idea of a moving Earth in the 16th century, the concept of inertia was not understood. There was much arguing and debate about whether or not Earth moved. The amount of force required to keep Earth moving was beyond imagination via Aristotle's theory. Now, another argument against the moving Earth was the following. Consider a bird sitting at rest at the top of a tall tree. On the ground below is a fat, juicy worm. The bird sees the worm and drops vertically below to catch it. This would be impossible, it was argued, if the Earth moved as Copernicus suggested. If Copernicus was correct, Earth would have to travel at a speed of 107,000 kilometers per hour to circle the sun in 1 year. Convert the speed to kilometers per second and you'll get 30 kilometers per second. Even if the bird could descend from its bench in 1 second, the worm would have been swept away by the moving Earth a distance of 30 kilometers. It would be impossible for a bird to drop straight down and catch the worm. But birds, in fact, do catch worms from high tree branches, which seemed to be clear evidence that Earth must be at rest. Can you refute this claim? I leave you there, and I hope you will leave your answers in the comment box below. I will see you in the next video. Bye!